Before looking at assembly code examples, let's talk a bit about how information is stored in the computer's memory. What follows, especially the first parts, may be review for you, but at least skim the transcript and be sure you understand all the ideas. So to start with, memory is described using two important terms, which you may already have encountered in other study: bit and byte. A bit is simply a 0 or a 1. A switch turned on or off. This may take different forms depending on the type of memory. In RAM, it may be an electrical charge held on a transistor. On a disk, it may be a north or a south-oriented magnetic spot on the surface of the disk. However it's stored, an individual bit may be either on or off. A single on-off or 1-0 value is the fundamental unit of computer memory. Now, of course, just a 1 or a 0 in memory is not all that useful. After all, how much can you say with a single on-off or 1-0? So these bits or switches are grouped into larger units. After a few experiments and adjustments in the early days of computer design, it's long since been settled that groups of 8 bits are the best choice, and such a group is termed a byte. You can imagine a byte as a bank of 8 switches. If you like, as I show in the diagram here, is a series of 8 1s or 0s. A byte may store any pattern of 8 1s and 0s that you like. And any computer memory, whether it's disk or RAM or otherwise, may be thought of as a long series of bytes. We really don't deal with individual bits when accessing computer memory. A byte is the smallest unit of practical use. And please be clear on the difference between these terms. I often find students mixing byte and bit, perhaps because of the similar sound. A bit is just a single 1 or 0. A byte is 8 bits. Now, grouping bits still doesn't answer the bigger question of how to use 1s and 0s, in groups or otherwise, to store the kind of information that is actually useful. Say numbers, text, or even more elaborate and less clearly numerical things like colors or pictures. How do we use this basic pattern of 1s and 0s to store such information? Well, the first example is highlighted here in the diagram. Counting integers in binary. Obviously, we often need to store numbers in a computer program, and we'll need to use 1s and 0s to do so, since that's all the memory has. Numerical values stored in a computer are represented in binary, or base 2 form. To understand base 2, recall the concept of place value that we all learned somewhere back in grades. A decimal number has a 1s place, a 10s place, and a 100s place. As we move to the left, each successive digit has a value 10 times greater than the one to its right. Binary or base 2 arithmetic works the same way, except that the place values, as shown in the diagram here, start with a 1s place, and then a 2s and a 4s and an 8s place. Each place value as we move left is multiplied not by a factor of 10 but by a factor of 2. In the example of 1101 in the diagram here, thus represents the value 13, 8 plus 4 plus 1. Now, you can get much deeper into a computer arithmetic in a computer architecture class, but let's at least try using this system to count a little bit in binary, starting with just 1 byte. We'll assign binary place values to the bits of the byte, as shown in the diagram, starting with the 1s place on the right, and then moving up all the way to the 128th place after doubling 7 times for the leftmost bit. This makes a byte into an 8-digit binary value. We can view this byte of all 0s, for instance, as representing the value 0. But if we turn the rightmost bit to 1, then we have the value 1. Setting the last 2 bits to 1, 0 is a little more interesting. That's not the value 10, but rather the value 2. There's a 1 in the 2's place and a 0 in the 1's place, and all the other places are 0, so the total value is 2. Setting the last 2 bits to 1, 1 gives us the value 3, a 2 plus a 1. And then if we increase that by 1 more, we arrive at 1, 0, 0. That's a 1 in the 4's place, and all other places 0. This is not the value 100, of course, but the value 4. You can think of the 1, 1 or 3 in binary as analogous to 99 in base 10, in that the bottom 2 places are totally filled, and adding 1 results in them flipping back to 0 and adding 1 to the next spot instead, the 4's place. Place values get filled really fast in binary. When you reach 1, that's like reaching 9 in base 10. So continuing on a few steps here, we have these values for 5 and 6, and so on. We can count upward arbitrarily using this system. The only digits we need are 0 and 1. You don't even need the digit 2 in the binary system, because if you want to represent 2 in a given place, you instead add 1 to the place value above it. Just as in the base 10 system, we don't need a single digit for the value 10, because if you want a value 10, you just add 1 in the next place up. So counting in binary allows us to use bits containing just 0 or 1 as digits. And we can count as high as we like if we have enough bits to do it. In fact, the term bit is an acronym. It stands for binary digit. So now that we've gone through this first question, please extend the ideas just discussed to count upward in binary to the value 20. Show an 8-bit value for each of the numbers 7 through 20. We've already done up to 6, of course. So if you're ready for an answer to that, here they are, from 7 up to 20. Now, since the rightmost bit has the least mathematical place value, it's generally termed the least significant bit, or just LSB. And likewise, the leftmost bit is the most significant bit, or MSB. We'll use these terms from now on. If we go all the way up to all ones in a byte, that's the highest value we could get using 8 bits. And it turns out to be 255. You can add it up if you like. The place values, of course, are 128, 64, 32, 16, 8, 4, 2, and 1. And they total up to 255. Now, this is probably a good place to bring up a block of vocabulary that I'll add to the vocabulary list for this lecture. You can see it here in the diagram. Those are the powers of 2, from 2 to the first, or 2, all the way up to 2 to the 16th, 65,536. Please treat these as vocabulary terms, meaning memorize them. You'll be tested on this. And it's not just tedious mathematical memorization. Those powers of 2 are useful to know. I'm a geek, but I'm not the kind of geek who memorizes numbers just for fun. Still, I have the first 16 powers of 2 memorized because they come up all the time in my work with computer software and hardware. So what if we want to count higher than 255? Well, we use more bytes. As I said earlier, we can always get more information from memory at least 1 byte at a time, but in fact, we often draw information from memory several bytes at a time. It's common, for instance, to use multiple bytes for larger numerical values. So we might store a larger number using 2 bytes, 4 bytes, or these days, as memory becomes even cheaper, 8 bytes. Let's see what happens if we count larger integers using 2 bytes, or 16 bits. We count in binary, following the same principles, but with a lot more bits to use. With 16 bits, the MSB, leftmost bit, will have the value of 2 to the 15th, or 32,768. And if you add up all of the bits, the total value of 16 ones is 65,535. Now that's better, and it might be large enough for some purposes, but we'll often need more. Let's see what happens with 4 bytes, or 32 bits. Now the MSB has a place value of 2 to the 31st power, or a little over 2 billion. Counting this and all the lesser bits, we'll find that 32 ones comes to over 4 billion. That's enough for most purposes, unless you're storing the national debt or something. You do not have to memorize that number, by the way, but you should know that it's a little over 4 billion. If you go to an 8-byte number, you get a maximum value considerably larger, around 10 to the 19th power, 10 quintillion, which one would hope should be sufficient even to store the national debt. Bytes are pretty cheap, so using them in larger groups is common. As we get deeper into programming, we'll see that patterns of data may occupy quite a number of bytes. So, summarizing, we can count up to all ones to get the largest possible value for a given number of bits. Those values for the most common integer sizes are 1 byte, or 8 bits, max 255, 2 bytes, 16 bits, max 65,535, 4 bytes, 32 bits, max a little over 4 billion, and 8 bytes, or 64 bits, max a little over 10 quintillion. A brief historical note before we close this lecture segment. Virtually all computers in existence use binary logic because it's the simplest to implement in hardware. But there's no law of nature requiring binary logic and arithmetic in computers. For instance, there have been experiments in the past with memories that have fundamental units with 3 different states, sort of on, off, and in between. This is called ternary or ternary logic, but it never turned out to be worth the added complexity.